Okay, so in this section 7.1, we're gonna be solving linear systems first in two variables, and in the next section in three variables. Now, here's a typical type of problem. So first of all, what is a linear system of equation? So what we have here is a typical type of problem that involves a linear system, right? So here, Gabriella and Jacob are selling cookie dough for a school fundraiser. Customers can buy packages of white chocolate chip cookie dough and packages of oatmeal cookie dough. Gabriella sold 2 packages of white chocolate chip cookie dough and 3 packages of oatmeal cookie dough for a total of $37. All right. Jacob sold 1 package of white chocolate chip cookie dough and 8 packages of oatmeal cookie dough for a total of $77. What is the cost of each 1 package of white chocolate chip cookie dough and 1 package of oatmeal cookie dough? All right, so here's a typical type of problem where we would need to develop some kind of system of equations that we solve simultaneously. Right now, if you notice here, a couple things that kind of stand out here. All right, so first of all, it's always helpful to figure out what is it that we're trying to solve. Well, we can find that in that last sentence, right? What is the cost of each 1 package of white chocolate chip cookie dough and 1 package of oatmeal cookie dough? So that is my unknown, right? So we have 2 unknowns, right? So usually when you have 2 unknowns, you're going to need at minimum 2 equations to kind of relate both of those unknowns, right? And the way we'll do that is right through the packages that, the packages that Gabriella and Jacob each individually sell, right? We know the number of them and the total dollars that each one of them cost, right? So, excuse me, setting up some variables, right? We can write an equation that tells us what Gabriella sold and an equation that tells us what Jacob sold. Right, so what I have here, I'm going to switch over to my sketch here. So what I have here is just that type of model, right? And this is what our system of equations will look like, right? Where the variable W is the cost of the white chocolate chip cookie dough. And the variable T is the cost of oatmeal dough, right? And as we see our first equation here, our first equation is what Gabriella sold, right? 2 of the white chocolate plus 3 of the oatmeal dough gives us a total of 37. While the second equation is what Jacob sold, right? 1 of the white chocolate chip cookie dough and 8 of the oatmeal dough for a total of $77, right? And this is typical of a system, right? We want to solve both of those at the same time. Right. Now, what does it mean to solve a system, right? Let's say, for example, that I came up with the solution of 5 and 9, right? Where 5 in my ordered pair is the W and the 9 represents the T, right? So the 5 represents the cost, right? Cost for white chocolate dough, right? Chocolate chip dough, right? And then $9 is the cost for oatmeal dough. Right, but what does it mean to solve the system? Right, so what it means, what it means to solve the system, right, is that when I take those numbers 5 and 9 and I plug them in to both of the equations, right, not just one of them, right? If it is a solution to the equation, then it has to give me 2 correct answers for each equation, right? Or let me say that properly. It should give me a true statement for each equation, right? So here we have 37 equals 37. So that checks off. That is correct, right? And then in my other one, we get 1 times 5 plus 8 times 9 equals to 77. And here, see, we get 5 plus 72 equals to 77. And here we see we get 77 does in fact equal to 77. So this is a solution to the system, right? Where that ordered pair 5, 9 satisfies both of the equations, right? And when we say a linear system, we mean that the variables, whether we choose X and Y, right, which is standard when we think of the abstract, just a system of equations, right? We choose the variables X and Y. Here, I made them a little more descriptive with W and T, right? But it's the same idea, right? So then here is linear, where the powers are 1, right? So the equation is a line, right? And then you may be asking yourself, well, is there another solution, right? Does 5, 9, will any number work? Well, as it turns out, this is a unique solution. This is the only solution that would work, right? And if I switch over to the graph here, and here you see here in Desmos, right? I use X for W and then Y for my T variable. And you see we do in fact have 2 lines for our linear system. And we have the solution is where it intersects, right? Where it crosses, and that happens to be 5, 9. Right now, if you happen to choose any other point that's on the line, so for this one, this will satisfy this equation, the one representing Jacob's cells, right? But it will not satisfy Gabriela's cells, right? So hence it will not be a solution to the system. It'll be a solution to this equation, but not to the overall system, right? So when you want to find a solution to the system, it must satisfy both of the equations, right? And we will only have 2 equations for 2 variables in this section here. Okay, and then later we'll see, we'll develop kind of ideas that every linear system falls into one of 3 categories that we're going to look at. It either has one unique solution, like we have here, it has 0 solutions, or it has an infinite number of solutions. And we'll go over the conditions that need to be met for it to fall into one of those categories. Okay, thank you.